All right. Here we're going through the start of the second half of last year's computer lab exam with the section that is metabolic modeling in MATLAB. I originally planned to do the whole thing in one session, but due to time constraints, I've decided to split it up into two different ones. And so, because of that, yeah, I'll just get started here. So, it's going to be 4 exercises. They're a little bit longer than most of the exercises that have been so far, but all in all, they shouldn't take, there's not that many of them, so they shouldn't take too long combined. So, the first one here is purely about reading in model.xml and then just quantifying some of the attributes of that metabolic model. So we have here model.xml, which is an XML file, and so we'll read that in by just doing model equals read cb model. We can specify the model name or file name as a string. We can also just have without the string, and then we would get a prompt, and then we could pick it out. But here the name of the model is pretty simple, so you might as well just type it all out. So here we'll get, like when we call it without the colon here, MATLAB will actually give us a lot of these numbers outright. So let's see what the exercise wants. So first is the number of metabolites, and we'll see here that that corresponds to the SMETS or field in our model structure, which is 1061 long. So we have 1061 metabolites. Actually, let's just label them. We have 1061 metabolites in the model. We have reactions 1266. I think that was the next thing. No, that's B. Okay, so see, we have 1266 reactions in the model. In terms of number of genes, 750. That's this field here. The model has 750 genes. And then we actually need to find exchange reactions and metabolites and molecules available in the environment. So this is slightly trickier. Here we can't just read it off network attributes. So there's 2 ways we can find exchange reactions. The first is by, arguably simplest if you know it, is just calling the exchange reaction or find exchange reactions function in Cobra. So if we do find X reactions of model, it will give us this Boolean array. So that will be either 0 or 1 depending on whether that reaction is an exchange reaction. Specifically, it looks at reactions where that only has positive elements in the stoichiometric matrix. So there's only metabolites on one side of the reaction, and that's how it quantifies an exchange reaction. So we might actually want to put this as a just store this into a separate array. So we can just say exchange equals find exchange reactions of model. And then if we look at that, that will just contain the output from that function. And again, since this is either 0 or 1, we can see if we go down here, we actually have a couple of ones here. We can do sum is exchange. That's just going to give us the sum of all these elements, which are either 0 or 1. That's 116. So we have 116 1 elements here, and that means 116 exchange reactions. We find 116 exchange reactions, and we can double check by, for instance, looking at the model here and then going into reactions and then just scroll down until we find the ones that are labeled X here, right? That's typically how a model will have exchange reactions labeled. So we see it starts here at 385, and it goes on until 500. So that's 500 minus 385 plus 1, because we're including both ends. That's 116. So it adds up. It's a nice double sanity check. That being said, this method here, where you just look at the names, is not foolproof. You can easily have a model that's somewhat poorly annotated, and that will that might have some exchange reactions that are labeled X at the start and some that are labeled X at the end, or maybe all are labeled at the end, and then you would have to count them all individually because they wouldn't be sorted nicely like this. So the reference way to do it is really using this fine exchange reactions model or the function here. So yeah, 116 exchange reactions. And lastly, we want to find the number of metabolites and molecules available in the environment. And now, if we look at our reactions here, all of these exchange reactions, let's scroll back down here, will correspond to one metabolite. So if we look, for instance, here at the stoichiometric matrix, we start about, what's the first one? 385, I think it was. Yeah, 385. So yeah, actually looking at the S matrix directly might not be the best thing, but if we can do, for instance, sum of model.S 385, maybe like other way around, maybe there should be, yeah, here we go, -1. So you only really just have one positive element there. And see what happens here if we do across the whole thing. Actually, 385. So let's do here 385 to what was it, 500 sharp, I think it was. And you see here, these are all 1, or all -1 rather, which means that for each of our exchange reactions, that exchange reaction corresponds to the uptake of a single metabolite. And so what we need to know in order to find the ones that are available in the environment is find all of these exchange reactions where we have a negative lower bound, because that corresponds to, the convention is that a negative flux through an exchange reaction represents an uptake into the system, while a positive flux represents a secretion. That's why all these elements here are -1. So when you create something, you have a -1 flux, or you have a backwards flux through a reaction that that destroys that metabolite. So yeah, we want. So what we can do is we can see, okay, which reactions can, with their current boundaries, model.lb carry a negative flux. So if we do that here, it will find model.lb. This will give us all reactions that are below 0. But then again, we don't necessarily know which ones here are exchange reactions. So what we need to do is we need to check both that model.lb is less than 0, and that they are exchange reactions. And we've already made our nice little logical struct here that is 1 for all the ones that are exchange reactions. So if we just do this, we find 6 exchange reactions with negative lower bounds, which means that they are reversible, which means that that metabolites can be taken up. So we find 6 metabolites available in the environment. So that's it for exercise 1. Let us now move over to exercise 2. So for this model, we want to find the optimal FBA growth rate. Let's just start with that before we move on to the next. So here we go. and then we do we just do sol, give it a name. Sol equals optimize. No, that's not it. Optimize. Optimize CB model. Let's just bring this up here a little bit. And so we see here what's relevant for the growth rate is this value of obj. That's the value of our objective function, which without double checking is the biomass. Let's actually just double check that that the objective function is the biomass. So we can just do find model.c. I think if we just do this, yeah, 1266, and then if we do model.reactions 1266, that is the biomass reaction. Nice. So yeah, the optimal value of our objective, which is growth, is 0.0973. So the FBA optimal growth rate is 0.0973, if that was correct. Yes, 0.0973. Okay. And then we want to find the metabolites and molecules actually entering the model. So we found in the previous exercise that we had 6 exchange reactions that could actually be taken up. And if we look here at our sol object, we will have this this x here, which is the value of each of our fluxes. So if we look at model, yeah, let's just sol, and then we go into sol.x, and here we'll see that most elements will actually be 0 and some of the fluxes will be non-zero. So we want to find the flux or the exchange reactions that also carry negative flux. So instead, previously we did to find the ones that could carry flux in the negative, we did find, so let's just go up here, model.lb, model.lb less than 0 and is exchange. Now instead, what we want to do is we want to do find sol.x less than 0, but also is exchange. And let's see what that gives us. Well, that gives us actually 5 of these exchange reactions actually take up flux, the only exception being 436. So let's see what's in them. Sorry. So here we see that the metabolites being taken up are glucose, NH4, oxygen, phosphate, and SO4. So we can just say the metabolites actually entering the model are, so what did we say? Glucose, NH4, O2, PI, and SO4. Yeah, that's really all that we're being asked for, and then their optimal uptake flux values. So here we will, and here in this case, as this exercise is phrased, it is perfectly fine to say what just what those x's are. We're not being asked for any sort of bounds here by FVA. It simply asks what are the flux values for these reactions in that specific optimal problem. So then we can just do actually sol.x here. And so we can do uptake rates glucose -1 gram per millimole, or millimole per gram dry weight. I think that is normally the standard unit here. For NH4, yeah, let's just remove the zeros here. They're not that important because we're actually talking about an uptake rate, and that is and that is a positive number, depending on how we look at it. Third was O2. That is 2.4338. Yeah. Phosphate was 00192. And last was SO4, which was 0.0075. And then we can just copy paste this at the end of everything. And so yeah, these are the main characteristics of the original optimal solution to this FBA model, with an optimal growth rate of 0.0973 and the following uptake of these 5 metabolites from the environment. Typically, you're not going to see too much variation in nutrient uptakes. Internal fluxes will often be quite degenerate in an optimal solution, that you can have tons of alternate internal pathways that are equivalent, but usually you will with exchange fluxes, certainly one of them will always be limiting, and that one will not have any leeway. And while the others you might have some, but in a case like this, where only 6, where we already have fluxes through 5 out of 6 of the ones we have, or the ones that we have available, that's normally because they're all necessary to a certain extent, although the bottleneck is going to be the glucose uptake here. So moving on to number 3, we want to find the number of reactions that are reversible, first according to the specified reaction bounds. That means which reactions are generally considered to be reversible. And we can do that by looking at the lower bounds as they're specified in the model. So we can do, if we do, first we can just double check that all of our reactions have a positive upper bound. That's something they should have, but theoretically you can have a reaction that is unidirectional, and for some reason that's only valid in a negative flux. I don't quite know why you would do that, but it's theoretically possible. So let's do that as a sampling check. So we could do find mol.ub greater than 0, and to count the number of elements there, we do just sum. Oop. That isn't quite right. Yeah, we don't want sum, we want size. So we do size, find mol.ub equals 0. That's 1,266 reactions. So all of our reactions, because that's the number we had originally, if we look here, 1,266 reactions, all our reactions have a positive upper bound, as they should have. So now let's do it the other way around. Find the ones that have a negative lower bound. Find like this. And we find 436 reactions with both a positive upper bound and a negative lower bound, which means they are reversible according to the specified bounds. So again, I'm being quite senile here, 436. So we find 436 reactions that are reversible under optimal, under specified reaction bounds. I got a little bit ahead of myself here. Okay, and now on the ability to carry flux under optimal growth, that's the second criteria we want to check for reversibility. And this is a bit trickier because we might have reactions that now have that might be in the general sense reversible, but that but aren't de facto reversible under the conditions necessary for optimal growth. Because if some reactions are simply necessary to either follow a very tight bound, or at least to generally work in a given direction, and working them in reverse would be detrimental to the biomass objective, and so that you wouldn't actually find them de facto reversible in a model. So the way we would identify this is with FVA. What FVA does is that it will, for optimal growth, it will give us the upper and lower bound. of the fluxes, of each flux, while still satisfying the requirement of optimal growth. So if we can just call them LB and UB, I think that should be the correct order, equals flux variability of model I need to double check that LB and that's actually the order they come in. That being said, this takes a little bit longer to run. Shouldn't take too long. It's actually a little bit slower than it usually is. For some reason, my MATLAB has been a little bit slow recently. There we go. So if we look here at LB, yeah, this is usually negative, and UB here is usually in the positive. Now, what we see here is we see actually quite a few that are non-zero but very low, and these could very well be just numerical errors. But let's disregard them for now. So what we can do now is we want to find all the elements where the lower bound is below 0 and the upper bound is above 0. And here it's we don't have the same as with the specified reaction bounds, where we can be pretty sure in advance, even though we checked it, that everything is going to have a positive upper bound. You might very well have fluxes that, according to flux variability, have a negative upper bound, because that reaction under optimal conditions it's a reversible reaction, which under optimal conditions will have to go in the reverse direction. So we can see here, for instance, 346. That is one of them. Of course, all our uptake reactions are technically defined in the negative, the ones that we saw in the previous exercise. And a glucose uptake, for instance, would not be, if we actually just look at that, I think it was like 4, yeah, let's actually, maybe scrolling up isn't the best idea. So if we look here at, here, what was it? This is model.reactions. And so 428, if we just do UB of 428, that's -1, right? So this is a reaction that for which the FVA upper bound is negative, which again you don't expect to see if you're looking at the just model bounds, but when you look at FVA bounds, then it's quite plausible for individual reactions to have negative upper bounds. So with that little digression sorted out, we now want to find the number. So let's start with the size. LB less than 0. Let's add some parentheses here. LB less than 0, and UB greater than 0. This doesn't seem quite right. Oh, I think we might want, let's just look at this here. No, I know what the problem is. We need to do size of find. Here we go. So find, if we do it without the size, I messed up my parentheses here. Yeah, this will give us all the reactions with negative lower bounds and positive upper bounds, which means that they are reversible in our FVA optimal solution. And so the size of this is 58. So we find 58 optimal, or reactions that are reversible under conditions requiring optimal growth. And so discuss the difference between A and B. I've sort of done that now, as I explained how we did B in the first place. But so we can summarize it as simply because a reaction is thermodynamically reversible, it doesn't mean that it doesn't have to go in a certain direction in order to enable optimal growth under a given set of conditions. Using FVA, we can find the lower and upper bounds for each reaction while still satisfy. Let's actually go for each for the flux of each reaction while still satisfying the possibility of optimal growth. This is important because ordinary FBA only returns one optimal state, but usually there are many equivalent optimal states, and it is possible that some reactions could go in either direction, could go in, let's say, different directions in various different optimal states. That's, yeah, essentially a decent explanation of the difference between these two and sort of why we care. The purpose of this exercise is a little bit to lead into this notion of FVA without specifically specifying it. And this notion of what fluxes are actually possible under optimal growth is something that should sort of trigger that instinct of, oh yeah, no, this is what we have FVA for. And so that's why FVA isn't specifically mentioned in the exercise, but the goal of it is to be able to pull out a little bit of a discussion on FVA on this topic. But it's not critical as long as you understand the difference between these two requirements and you know how to actually call the FVA function to solve question B. That is good enough. Okay, on to the fourth and last question we will be going through in this session. Perform single deletion analysis on the model from problem M1. Classify genes as follows: non-essential if mutant growth rates are larger than 95% of wild type, essential if mutant growth rates are less than 5% of wild type, and intermediate if the growth rates for the mutant are between 5 and 95% of the wild type growth rate. So the first is just how many genes do we have in each category. So the first thing we want to do is we want to perform a single gene knockout analysis. Don't say it. Indeed, genes is what we're looking for, and find the growth rates for each of these mutants. So if we just do, let's call it just single del equals single gene deletion of model. It's going to take a few seconds. Okay, and if we here look at single del, it will give us a 750, that's the number of genes we have, length vector of values between 0 and 1. And so first we want to find all the ones that have that we consider essential. That means that the growth rate here is less than 0.05. We said 5%, right? So then we can do size find single del less than 0.05. Yeah. listen here. Find single. Did I not? Oh, it was the other way around. Whatever. Okay, let's just do it again so it has the right name. I could have just renamed the variable, but it's done now. Okay. So let's just recall what we had from earlier, size. And here we find 105 genes have single mutant growth rates of less than 0.05. So we find 105 essential genes. And then we can do the same and just say less than 0 or greater than 0.95. That's our criteria for non-essential. 603 non-essential genes, and then some basic math should give us 750 minus 708, 42 intermediate. Let's just double check. Size, find single del greater than 0.05. Let's replace this with a less than sign. I think my parentheses should be balanced, and yeah, that is 42 genes. So, and 42 intermediate genes. So the second question is, how reasonable are the choices of 5% and 95% as cutoffs for non-essential and essential genes? This is one where there's not like a clear-cut right and wrong answer. This is one of those questions where you're not going to be judged on your conclusion. You're going to be judged on your ability to discuss and come to grips with the problem and show that you have an understanding of what these numbers represent. I would say that 5% and 95% are quite strict in terms of cutoffs. Certainly, I would say that maybe if we went up to 10, maybe even 15% as the upper bound for non-essential, that would be quite valid or valid as a qualification for essential, since such a mutant is never going to survive in any competitive environment. It's going to be outcompeted by non-mutants quite handily. Although, if, say, we're looking at an organism for which, say, if you're trying to do FBA of cancer cells or something where you truly want to find a mutant that gets rid of them, root and stem, you might want to be somewhat stricter. Similarly, 95% as the upper cutoff for non-essential is quite strict as well. If something grows at 90% of the wild type, it's gonna come off as quite healthy on its own. So we can just say the choices are quite strict. A mutant that grows at 10% would probably be outcompeted by non-mutants in a real environment and not be able to thrive, although for purposes where one wants to ensure that the mutant truly disappears, one might actually want to set a strict 0% mutant growth ratio requirement. Similarly, a mutant growing at 80%, 90, let's say 90%, or even 80, 85% would often be able to thrive quite well. Something like that. The main idea here is to be a little bit aware that there is no easy solution to say when something should be considered essential or not. Of course, if something is 0 or something is 1, then you can say hard and fast what it is. But sometimes you don't set this intermediate regime. You just say everything that's below 0.5 is this, everything that's above is non-essential, or you can set that at 0.3, or really whatever you feel like it's something you'll have to justify for that specific case. And the question now being, part C here, would our results in A be severely affected if we chose different cutoffs? Justify your answer. Well, let's look at this now. So, if we now say that we want to find the ones that are let's just do single del, and then of all the single dels that are, I think this is how we call unequal, not 0. I'm gonna need more parentheses, and all the single dels that are not 1. I think this should do it. Yeah, for some reason I called it with the wrong name. Okay, so it returns us some 1.00 here, which really should be 1. But all the rest here are the different growth rates that are neither 0 nor 1. So the first is we see that very few of these are very close to 0. Quite a lot of them are very close to 1. Some are indistinguishably close to 1, some are okay 1% below, maybe even less. What we have no, still 1% below, 10% below. But we see that all of these, in very few of these cases would we get very different results if we say something else. So if we say, for instance, if we were to set our limit to 10%, for instance, or 90% growth for something we consider non-essential, how many did we find originally? We found 603 non-essential if we set 95% as the criteria. If we say size, find single del less than 0.9 or greater than 0.9, for instance, 607. So by changing that criteria from 95 to 90%, we have 4 genes that have been rebranded, which would be this one, these 2, and this one, I suppose. Yeah, that's it. So anything smaller within that regime would not really have a great effect. And if we do it the other way around, if we try to find the number of single gene deletions where the fitness is less than 0.1 instead of 0.05, as we said earlier, we still have the 105 that we found previously. So we can say that we find that none of the that no mutants have growth rates between or let's say larger than 0 than 0 and simultaneously less than, I think, what's the lowest we have here? I think it's this 4186. Yeah, and less than 0.4186. So most reasonable variations on the lower cutoff would not have a significant effect. If we look at the upper cutoff, oh, wrong window. If we look at the upper cutoff here, if we were to set it to 90%, or maybe if we were to set it to, let's see what we say here. If we're quite generous and we say greater than 0.8, 610. So if we compare to 603, for the upper cutoff, distinguishing non-essential from intermediate, we find that even a substantial change in the threshold to 0.8 would only lead to I think 7 more genes for a total of 610 being labeled non-essential. And by and large, I would say that this is a pretty minor effect. It's a 1% change in the number of essential genes. So we can be quite comfortable with the choice of 5% and 95% as cutoffs, as even moderate to large changes in thresholds has a reasonably small effect on the number of genes in each category. Yeah. So that's it really for this session. Some initial FBA modeling. Just looking at a model, running some simple analysis on it. Nothing too time consuming, nothing that requires the really hairy functions or things that are outside of standard MATLAB. And just really the core Cobra functionality with a little bit of secondary MATLAB, things like the size and find functions that are useful to know in terms of just quickly counting and identifying certain elements in the matrices. I imagine that maybe for some of these you could call some Cobra functions directly. I prefer to stick to the core functionality as much as I can. I'll often, instead of using Cobra functions to change objectives and lower bounds, I'll actually just change the upper and lower bounds directly, but those things are quite equivalent. So yeah, that will be it for now, and I will be back later with the last third, I guess, or quarter, depending on how you look at it, of last year's computer exam. Thank you.